Hi, previously we talked about the formula for calculating the gravitational force. Today we're going to move on and talk about the gravitational field strength. My students in the past always find the field strength always the hardest part in IB physics. So here, let me try to simplify it to you. So make sure you write down some notes and hopefully that can help you in the future. So first of all, whenever we talk about field strength in IB physics, there are actually three kinds only. And here, of course, we have got the gravitational field strength. The other two kinds that you have probably have learned before is called the magnetic field strength and electric field strength. If you want to understand the general idea of field strength, I'll recommend you to understand all these three field strengths all together. Then you have a better understanding. So first of all, let's try to think about what are the common things about these three field strengths. The answer is they are all referring to the force that a substance can experience based on their physical properties. Okay, so probably you still don't understand. So other than looking at the common things on the field strength, we should also look at the different thing about the field strength. So think about gravitational field strength. It is referring to the force experienced by the mass you have. So the more mass you have, you experience a greater gravitational force. So what about magnetic field and electric field then? For magnetic field strength, you can recall what you learned in IGCSE, the left-hand rule. So FBI was the thing that you do, and to deduce the force which can be induced with the presence of the B field when you have currents, right? And so that means the greater current you have, the greater force that you can experience under a certain magnetic field. So this is something to do with current. Okay, so like again, gravitational field, the more mass you have, then the greater gravitational force you have. For magnetic field, then the greater magnitude of currents you have, then the greater magnitude of magnetic force you may experience. And so for electric field, this is something that when we mention the static charges, so positive charge or negative charge. So obviously, this is something to do with the charge itself, like how many coulombs of charge that you have. So more charge, then you have a greater electric force. And so this is basically the idea, because when you try to look at the unit for gravitational field strength, it's going to be Newton per kg, because it's force per unit of mass. So for example, on Earth's surface, it's going to be 9.81 Newton per kg. So if I am 70 kg, then I'm going to do 70 times 9.81, and that will be the force that I experience given by the Earth. And so for the other two field strength, you will get to learn more about it in other chapters. So it looks pretty easy, isn't it? So let's take a look here. So for gravitational field strength, similar to gravitational force, there is also a word definition. I'll recommend you to jot it down somewhere and try to find a way to remember it. And the thing that I would strongly recommend you to emphasize to yourself on your notes is, other than saying gravitational force per unit mass experience, one of the concept that people usually overlook is here: small point mass. NANI? So you should have a question: what exactly is small point mass? Think about this. This is a diagram of gravitational field strength of a planet, probably. So the direction of the arrow is representing the force that you may probably experience. So for example, if I am here, then obviously I will be attracted towards the planet. So that's why you can see the arrow is pointing towards it. And no matter if I am here, it's going to be the same. I will be attracted towards the planet. So all the arrows nearby representing the gravitational field strength is always going to point inward towards this planet. Similar to what you have learned earlier, the greater density of the field lines here will represent a stronger magnitude of the field strength. So that's why if you try to find a unit square or a unit space here, you find out this is much denser than the same amount of space that you try to square out, and obviously here will be of a stronger, greater magnetic field strength. I mean greater magnitude. So here, if you have another mass that I put here and try to experience its gravitational field strength, but then that is not a small point mass, instead it's a big mass, then what happens is, of course, this big mass is going to also have the gravitational field strength around it, and because it's really big, then it's going to affect the field strength that you have in this diagram. So the field strength would no longer be like how it was earlier, and it's also impossible to account for the gradual change. So obviously here, if it's closer to the original planet, it's going to be stronger, and if it is further apart, then it is weaker, obviously. And so in order to simplify the whole model, then whenever we talk about the field strength, then we always talk about the small point mass for gravitation. And later on, when you learn about electric field, then we'll be talking about small point charge instead. So this is the idea that we have to understand and mention whenever you have to recall the definition. And so alternatively, you can also interpret the small point mass as in they have literally zero volume, so they don't occupy any space at all. Of course, this is a theorized ideal mass. It doesn't really exist in our reality. Okay, so if you understand the new ideas that I just introduced to you in this video, you should be okay for the rest of the video, because this is going to get easier and easier for the rest of them. Next question. Why would the gravitational field lines around a planet like this is going to be radial? However, when we try to look at the gravitational field strength on the Earth's surface, for example, it's going to be parallel lines like this. I'll give you 10 seconds to think about it. The answer is simply you have to zoom in. So think about this as a planet which is large enough, and these are the gravitational field you can draw around it. If you try to go closer, if you only look at a certain part, or if you can imagine the lines are denser equally around the planet, then if you only look at a tiny part of surface, then they are more or less parallel lines. So that is to say, this line and the line next to it is more or less parallel if you only look a small portion and close enough. And so you may say, hey, then that means this diagram is actually a lie because they are not perfectly parallel. They are not truly parallel. They are just close enough that they look parallel. And yes, that's true.
You lie to me!
Okay, another concept done. So finally, we can go straight to the formula. So the formula is very simple, and actually I mentioned already, G is the gravitational field strength, and that is force per mass, and that is the formula simply. This is the definition. Okay, and so by applying the gravitational force, which is F equals to G m big M small m, or m1 m2 over r squared into it, then you can obtain this equation. All right, if you don't know how it can be done, Okay, just let me show you. G equals to F, which is big G, M1, M2, or you can use big M, small m, over R square, divide one of the m, right? This m. And so this m is referring to, it could be a person on the earth. So that's probably be m2. Alright, so we have to, it doesn't really matter actually. So these two will cancel out. Eventually, you only have G m1 or the big M over R square. So you would have, of course, this is referring to, for example, for Earth, it's going to be the mass of the Earth. And again, notice that the unit of gravitational field strength is going to be Newton per kg. Now, I would like you to do a very simple but satisfying task. Try to substitute the mass of the Earth and the radius of the Earth into this equation, and guess what? You should find the G, I call this small g usually, which is the gravitational field strength, to be 9.81. So try it out now.
A few moments later.
And it does. Okay, 9.81036. Okay, I mean there are other factors that we talked about circular motion earlier that affects G. And so I guess we can just take the first 3 digits and I guess we are happy with it. So again, the unit is Newton per kg, which of course, if you recall what you learned about mechanics way earlier, this unit is going to be equivalent to meter per second square. However, whenever you refer it as gravitational field strength, I would strongly recommend you to use Newton per kg, because even though it's equivalent, but in terms of physical meaning, Newton per kg is much more suitable. So finally, we can move on to do 2 example practice. Please pause the video now and try it out yourself first.
2,000 years later.
Alright, first question, there's another planet that you want to compare with the Earth, but its mass is 10 times greater. So I would say try to write down an equation about that. So I can say ME, and so equal to that whatever planet MP, but then the MP is much greater, so that will be 10 times of the mass of the Earth. So this is the equation that I will write. The other one is talking about the radius is 20 times as large. So if RE is the radius of the Earth, then RP is the radius of the planet, and this one is 20 times of the one with the Earth. So I would strongly recommend whenever you see this kind of question, when you try to calculate the ratio, you should firstly translate the word equation, the word of the questions, into this equation. So then this will help you to solve the questions later on. And so for now, what we have to do is simply express the gravitational field strength of both planets. So just recall what we learned earlier. Then the small g equal to big G m over R square, and this m of course is referring to the its own planet. So if this is Earth, and this should also be Earth. Meanwhile, this is exactly the same thing for the planet P, and so I will just simply write it down again. Okay, and as long as you follow this pattern, it should be all easy for this kind of question. So the next thing that you want to do is to apply what you wrote down earlier into this equation. So I would probably just write down GP is going to be big G, M is going to be equivalent to 10 of the mass of the Earth, and then for radius is going to be 20 times of the Earth radius. And let's not forget, when you bracket, you have to bracket both 20 and the Earth radius. Okay, and then square. And so the next thing that you can do is simply simplify it. So you can have GME over RE square, and while this is the coefficient, you can take it out, so that will be 10 and also 400 down below. And now if you look at this whole thing and then this whole thing, they are exactly the same. And so what you can do is simply change it. Okay, I don't have enough space, so I'll write here. The gravitational filtering of the planet would equal to the gravitational filtering of the Earth times these coefficients. So this will simply be 1 over 40, or I can multiply 40 on that side. Well, depending on what they want. They would want the exact number, then I guess, yeah, I can do it this way. So that should equal to Earth is in fact, well, actually no, not really. I can do it here, right? And then for the Earth, let's just keep it simple. Okay, let's just keep it as 10. So that will be 10 over 40. That is going to be 0.25 then. Again, the unit is Newton per kg. And so you may ask, hey, does that even make sense? Because this is so small. So you can think about this. The mass, yes, is much greater, 10 times greater, but then the radius is 20 times larger. And not to mention, radius is a more dominating factor than the mass because you have a square here. So that's why eventually it will be much smaller than the one you have on Earth. Okay, next it asks you to calculate the acceleration of free fall at the height. Well, basically, acceleration of free fall basically is the gravitational field strength. So we can simply use the equation gm over r squared, and it's at 300 km from the surface of the Earth, and it's given the radius already and the mass. So a bit similar to what we did just now for finding out 9.81, but then this one obviously is going to be less than 9.81 because it's slightly greater than the radius. So here what we have to do is we need to substitute everything basically, and so we should be able to find g equals to this equation. And just to remind you again, you have to add the extra height that mentioned by it. So plus 300 times 10 to the power 3 because it's km, and I know it's not going to be a lot. If you think about here, this is 10 to the power 6, so in fact 10 to the power 3 doesn't mean much, but then if you try to use your calculator, you'll be able to find the answer to be this 8.9 something, 8.968. okay, I guess I'll take 2 sig figs, so 9.0 actually. Alright, because this one is 2 sig fig only, or yeah, or you can take 3 sig fig 8.97 if you like to. In acceleration, so this time I would do meter per second square. And so you may be asking, hey, isn't they finding out acceleration? Why do I still express it as g? If you don't mind, you can do one more thing, as in thinking about the free body diagram. So that is only weight. So you can think about F equals to ma, and the only force is simply mg, and not to simply take this g for granted. That is 9.81 because 9.81 is only true when you're on the surface of the Earth. And so now you can't say 300 km away from surface is still surface on the Earth. So ma, and therefore the g that we find out is simply acceleration. So I guess with this, then we can claim this is acceleration. So I think this is probably the best presentation to say the answer will be 9.0 in meter per second squared. So that is the acceleration that you may have. And that is to say, if you try to skydive, then initially the acceleration is not as much than when you get close to the Earth. However, is it really possible to skydive at such altitude? The answer is not really. In fact, for the plane, like if you're taking a flight, then the altitude that you may have is around maybe 10 to 20 km only. That's probably the best altitude that they can travel because of the fuel, and it's very complicated when you try to learn like the best altitude for plane to cruise. That could be another video, or if you like to study aviation, then that's something you may want to study. Anyway, if you look at this diagram, then you can see the atmosphere actually is up to 90 km only. So if you go up to 300 km, in this question, this is already out of the atmosphere, and in fact that's the altitude could be for the satellite, because as you can see here, it's about 160 to 2000 km. So yeah, probably you can't skydive at that altitude. The highest skydiving that so far we have in the history was back in 2012, which is a skydive sponsored by Red Bull, by the way. The height was 39 km, and it was actually magnificent because it took a really long time to do the skydiving, and more importantly, it actually reached the speed of sound. So you can see here, it reached the so-called 1,357 km per hour, which is Mach 1.25. Mach number means the ratio to the speed of sound. So this is basically 1.25 times of the speed of sound. And so that person physically experienced the sound barrier and simply breaking the speed of sound, which is an enormous achievement for sure. But then anyway, it's still 39 km. So if you talk about 300 km, it is pretty impossible, because then it will be much more physically challenging, and not to mention this one. So if you are interested in this, you should definitely go to check out the footage of that skydiving. I watch it in real time, by the way, and so that's definitely something you want to take a look as well. And it is actually very interesting to see how they get him to prepare for this skydiving, what kind of equipment that they need, and what kind of system they have to ensure everything is ready and safe, and also his clothes as well, because like throughout the whole motion there will be a lot of air resistance, and that will create a lot of heat on the surface. So that is very important. And also looking at how initially he kind of lost the control, so keep rotating, and that was very physically challenging for his body. I think there was an interview saying that he feel faint, basically, like not even conscious, like at the very beginning, and then he recovered to be conscious again. And I think that's very important, because he got to launch the parachute, otherwise he will be dead, obviously. Oh, by the way, you can also see here, this is the oxygen supply that remaining. So it's very interesting. You can't. That means he cannot go too slowly, because he will be running out of oxygen. But he cannot also go too fast, because that's not going to be good for landing, obviously. So it's going to be very tricky. He got to know when to launch the parachute. I will put the link in the description below. You can check it out later on. That's all for this video. I hope you enjoy learning physics with me. If you do so, please hit the like button now and subscribe to my channel. I will see you again in the next video. Bye.